The perturbation theory approach allows us to relatively easily calculate corrections to the energy levels. Let's see what it has to say about the wave functions themselves. Now, I've rewritten up here a copy of the equation that we got to when we collected terms that were first order in lambda in the perturbation theory expansion. And from this equation, when we set m equal to n, we were able to derive that first order correction to the energy levels. So the question that we want to ask now is, what happens when m does not equal n? What happens here? Well, right off the bat, we can see that this term here must vanish because delta mn is going to be 0 when m does not equal to n. Now what I want to do is I want to move this term over to the other side of the equation. So when we do that, we'll end up with an equation that looks like this. We'll have psi m 0 h1, which is the perturbation part of the Hamiltonian, psi n 0 is going to be equal to a sub m times the difference between en 0 and em 0. Now if I divide both sides of the equation by this, I'll end up getting a result that gives me an expression for those coefficients a sub m. So a sub m has got to be equal to psi m 0 h1 psi n 0, then divided by the difference in the zeroth order energies, en 0 minus em 0. Now you'll notice right off the bat I've got something in the denominator here that looks like it could be 0, but we've chosen m not equal to n, so as long as we can stipulate that these energies are not equivalent, that is to say, we don't have a degeneracy in our zeroth order system, then this is a upstanding, fine result to get for this particular eigenstate. Now, when we use these coefficients, remember they are expansion coefficients when we're expressing the first order correction for the wave function in terms of the zeroth order wave functions. So now if I want to take that and use it in an expression to find what is my corrected wave function, the total wave function then would be approximately equal to the zeroth order wave function plus a sum over the zeroth order wave functions of these coefficients. So now I've got to put this term in here. Divided by en 0 minus em 0 and times this function. All right, so this is how that first order corrected wave function would look. And I've written these squiggly lines for the equal sign because this isn't exact. This is just the first order correction, and one can go to much higher order corrections. So we've essentially inserted a sub m in here as the expansion coefficients for this particular expression for the first order correction to the wave function. All right, now I want to make some observations about this. Okay, so we'll collect those over here on the side. First of all, notice that in this summation we cannot include the term psi sub n. Is that a problem? Well, if it were included, then the denominator really would be equal to 0, and it would explode and be an infinite contributor to the corrected wave function. But the fact is we've got psi sub n 0 represented over here, and so this is just a series of coefficients adding up the other functions. So one way to think of this is that the corrected wave function can only be a correction if it's adding things that are not already part of the zeroth order wave function. So these are all those other parts. They're all the other functions that belong to the full set of eigenstates of the zeroth order Hamiltonian. So in principle, it's found that this does not affect the accuracy of the perturbation theory. All right, another observation that we might make is the following. think about this term that's in the denominator of those coefficients. When this is a small term, in other words, when this is very small, it's in the denominator. Well, when you put a small thing in a denominator, it makes the overall thing larger. So that means this is for a larger contribution to the correction or to the overall wave function. Similarly, I can make a complementary observation that when this is large, then its contribution will be a smaller contribution. All right, so this is telling us something very interesting about these states. We can think of this in the following way. You imagine that the system started off as the 0th order Hamiltonian system, and then we gradually turned on the perturbation. Essentially what we did was we turned on an interaction between the states, the 0th order states of that 0th order Hamiltonian. And as we turned that on, the states that were closer in energy, that is where their energy difference was smaller, those ended up being bigger contributors to the correction in the wave functions. So one way we can think of this is that these things are telling us which states are likely to be strong contributors to the correction in the wave function. I should also note that the value of the numerator, okay, which is this cross term, these are the terms that are not included in the calculation of the first order energy correction, but these tell us something of something about the interaction between the 0th order states via this perturbation term and the Hamiltonian. So the value of this moderates the size of the contribution. All right, so this is something that we're going to see in other ways when we start talking about molecules and the way those orbitals interact, because these ideas from perturbation theory, it turns out, are going to actually be very suggestive of the sorts of things that we think about. So we can think of this, in a sense, as being like a coupling strength between the different 0th order modes. It's a coupling strength that determines how strongly the correction to a 0th order mode will come from another 0th order mode. Now I want to finish by talking a little bit about helium and how perturbation theory can tell us something about helium. So the first thing to do is to write down the Hamiltonian for helium. And to do that, what we'll need is to write in atomic units the following. So I'll have -1/2 Laplacian squared for particle 1, electron 1, 2 over R1. So this is basically a single electron Hamiltonian for one of the electrons around a nucleus that has a charge of +2. That's what the 2 in the numerator is doing there. Then we have another electron. So we'll have exactly the same sort of Hamiltonian for that one. So essentially I have 2 0th order Hamiltonians here, as though the 2 electrons were completely independent of one another and not interacting at all. And then we add the one term that is the interaction between them, which is the Coulomb interaction that's moderated by the distance between those 2 electrons. Now the 0th order energy levels in this case in atomic units are just going to be minus, and I'm going to use z squared over 2n squared, where z is the charge on the nucleus. Since we're using helium as our example here, I'm just going to go ahead and plug in 2. So that's going to be 2 squared is 4 divided by 2. So these energy values would be -2 over n squared. And if we're talking about the ground state, that means it will be -2 for each of these 2 0th order Hamiltonian pieces. All right, so what does that mean? It means that the 0th order energy for our overall system, so maybe I'll call that total 0th order energy for 1, is going to be -2 -2 or negative 4.0. So this is sort of what we want to judge against when we talk about the energy levels of the helium atom. This is what it would be if there was no repulsive interaction, Coulomb interaction between the two electrons. So now when we use perturbation theory on helium, we can, and I'll skip the tedious details, but what we can find is that the first order correction, and remember this perturbation Hamiltonian is just 1 over R12. It's just this term. Okay, when we do this calculation, we find that this is equal to 5/4 for this problem. All right, or 1.25. So now if we add that to this, we would find that to first order, the energy level is roughly equal to -4 plus 1.25, or minus 2.75. Okay, well that's one possibility. It turns out that we can exercise perturbation theory to much higher orders, and Shear and Knight have done this, and I'm running out of room, so I won't give you the full expression, but they give the terms all the way up to fourth order in perturbation theory, and the result that they get is that the first energy, the lowest energy from fourth order perturbation theory is minus 2.9037 atomic units. And this should be compared with the exact result, which is minus 2.9033. So we can see at this point we're getting results that are actually in pretty good agreement with the exact agreement for the helium Hamiltonian. So perturbation theory, when you take it up to high enough order, can give you good results. Now this is presuming that everything is well behaved and that the assumptions of perturbation theory are valid, but I think it is a good signal that even though this is not a Hamiltonian that we can solve exactly, we can still use our ingenuity to come up with approximation methods that give us a good result.